Okay, 1989 BC3. Consider the function f defined by f of x is equal to e to the x cosine x with a domain of 0 to 2 pi. First, we want to find the absolute maximum and minimum values of f of x. Well, absolute maximum, absolute minimum, based on the extreme value theorem, will occur at either critical points, critical values, or endpoints. So the first thing we want to do is find the critical values of that function. And we start with f prime of x is equal to, we have a product, so we're going to need to use the product rule. And that's 1 d2 plus 2 d1. We want to simplify that just a little bit. And that would be e to the x cosine x minus e to the x sine x. If we factor out the e to the x, we'll end up with e to the x times the quantity cosine of x minus sine of x. Then to find the critical values, there are no points, by the way, where this derivative is undefined. E to the x is defined for all x, cosine x, sine x, all defined. So any composition of those different functions will also be defined for all values of x. So where will f prime of x equal 0? Well, f prime e to the x is never equal to 0. So it will only be 0 when cosine of x minus sine x equals 0 or cosine of x equals sine of x. Cosine x equals sine x in the first and in the third quadrants when for reference angle pi over 4. So we know our critical values, and then we just need to test the original function at the endpoints and the critical values. F of 0 back to the original function is 1 times 1, which is 1. F of pi over 4 gives you e to the pi over 4 times square root of 2 over 2. F of 5 pi over 4 is going to give you e to the 5 pi over 4, and cosine of 5 pi over 4 is negative root 2 over 2. And finally, f of 2 pi is going to give you e to the 2 pi, and then cosine of 2 pi is 1, so that's that. So we can see from this we have only one negative value, so that has to be the absolute minimum. And because e to the 2 pi is going to be much greater than e to the 5 pi over 4, then e to the f of 2 pi has got to be our absolute maximum. In part B, we want to find the intervals on which f is increasing, and that'll happen whenever the first derivative is positive. So we're going to set up a sign chart from 0 to 2 pi, plug in our two critical values at pi over 4 and 5 pi over 4, and then we pick some test points in there. And I'll use pi over 6, pi, and 3 pi over 2 because it's relatively easy to evaluate the cosine function there. But all we really need to know is the signs. So plugging in pi over 6 into the first derivative, which is up in the top right corner, e to the x is always positive. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Root 3 is greater than 1, so that's positive. Plugging in pi, cosine of pi is negative 1, sine of pi is 0, so that's going to give me 0. It's going to give me a negative. Cosine of 3 pi over 2 is 0, and negative sine of 3 pi over 2 is negative 1, which is positive 1. So that'll be positive. So f is increasing when x is between 0 and pi over 4, or when x is between 5 pi over 4 and 2 pi. And that does it for part B. In part C, we want to find the x-coordinate of each point of inflection. Well, I'll go back to the first derivative in unfactored form. And I have e to the x cosine of x minus e to the x sine of x. And we need to find the second derivative. Well, our original function was e to the x cosine of x, so the derivative of that piece is just the first derivative. And then minus the quantity. Derivative of e to the x sine x is a product rule, 1 d2. That's e to the x cosine of x plus 2 d1. And that'll be e to the x sine x. When I simplify that out, the e to the x cosine x's cancel, and I end up with negative 2 e to the x sine x. And that will be 0 whenever sine x is 0. And that'll be at 0, pi, and 2 pi. So we're going to make another sign chart with 0, pi, and 2 pi. At pi over 2 it's negative, at 3 pi over 2 positive. So there's a point of inflection at x equals pi. And that does it for this problem.